This is Precalculus Concept 22b. This is our last video from the exponent and log unit. We're going to look at an example now of exponential decay. And one thing I want to emphasize is the exact same thing that you did with exponential growth. The one difference is that the k we end up with is going to be a negative number, which means that the growth rate is negative, which means that your quantity is getting smaller instead of getting bigger. Keep in mind our formula is going to be exactly the same, so I'm going to start with the same exact formula, and our job is the same. We want to figure out the initial amount and the value of k, and if I have those two things, I have a model that can be used to answer any questions. So we're going to look at a half-life problem. A half-life problem is a typical example of exponential decay. Most of you may know from your science classes that if you have a substance, over time it gets smaller and smaller and smaller. Some substances decay or disappear or become smaller very, very, very quickly if it's radioactive. It might be gone in seconds or nearly gone in seconds, while other elements like carbon, for example, take a really, really, really long time to decay and become less and less and less. So if I have a year that gives me the half-life, that's the amount of time that it takes, let's say 10 pounds of that material to become 5 pounds. So if I had 10 pounds of carbon and I buried it in the ground and came back 5,715 years later, I would expect that there would be about half of it remaining. Different elements have different half-lives, but a lot of older living animals that have carbon in them, this is how we figure out how old they are. Okay, so what's a little tricky about this is there are no given amounts, right? It doesn't say 10 pounds, it doesn't say 5 pounds, it doesn't say 1,000 pounds. The good news is you can make up any number you want for your initial condition. I like to use 100, thinking in percent, so at the beginning I have all of it, and I can figure out that by plugging in my half-life, which is 5715, my substance becomes half of what I started with, so that's going to end up being 50 in my example. Now you can choose any number you want. You could have chosen 8 as your initial amount, then 4 would be your half amount, right? So it turns out not to matter because your very first step in solving this problem is going to be to divide and isolate your exponent, and hopefully you'll see that whatever choice you made, you'll end up with 1/2 on the left. So I get 1/2 equals e to the 5715t, and by natural logging both sides, I get the log of 1/2 equals 5715t, and my t value is going to be log of 1/2 divided by 5715, and that equals approximately negative 0.000121. I get a negative number. Remember, that's not surprising because it's a decay problem. I would expect that. It's also a very, very, very small number, which also is not that surprising because it's decaying very, very slowly. Remember, this number represents your growth rate, so that's a very, very small growth rate. Alright, so let's look at our model now. So I have a final version. I have 100% of my substance times e to the negative 0.000121. T is something I can use to figure out, in this case, the age of any substance that I was interested in, right? So you may have heard of the Dead Sea Scrolls. These were discovered in 1947 as one of the oldest forms of writing, and it was determined that currently, there was about 76% of the original carbon left after many, many, many years. So the question is, how old are the Dead Sea Scrolls? So in this case, my 100% was my starting amount, and the 76 is what I ended up with, right, after a certain amount of time, and that time is what you have to figure out. So this is how you should start the problem. Plug in 76 for your answer, and your goal is to solve for t. You're going to see the steps, again, are very similar. This is just like last problem. The only difference is I have this kind of weird k value that's pretty small and negative. But when I plug it in, I'm going to jump a step here and do the log of 76 over 100 equals negative 0.000121t. And my final answer of t, I'm going to go ahead and do that work on my calculator, but I'm going to do that logarithm, get that answer, and I end up with 2268. Right? So in this case, my discovery is that in 1947, based on the amount of carbon in the sample, it was determined that the Dead Sea Scrolls were about 2,268 years old. Alright, so take a big picture look at this. Again, we're starting with the exact same formula. We're using the exact same steps to solve for k. Once we have k, we have a model, and we can use that model to answer a question, which once again resembles the same steps. So while difficult, once you catch on, these problems start to resemble each other very closely. Alright, we're going to jump straight to a U-try. This time we're going to talk about lead, which has a half-life that's much, much shorter than carbon. A piece of lead will decay to 1/2 of its original amount in about 22 years. So your question is to find the model, exponential decay model for lead, and then use that model to figure out how long it would take to decay to 20% of its original amount. And let's give your answer to the nearest year. Okay, think about that. Again, the hint I will give you is we're starting off with the same formula, and the a sub 0 is anything you choose. I would recommend 100, but you can use any number you want. Your job is to figure out the k value, and once you have that, answer the question. Alright, again, quite a bit of work here, but let's just run through the steps. You want to start with your original equation. Your a sub 0 can be anything, but you should keep in mind that your first number here, 50 in this case, should be half of whatever your original thing was. And your very first step, regardless of what you chose, you should have a half in that spot right there. Solving for k yields that decimal. It's again a negative number. That's expected because it's exponential decay. And it's quite a bit larger than our example for carbon, because the decay is much quicker, right? And so it's not taking as long. In this case, decay rate is larger. Okay, I'm going to go back to my original equation. Again, your initial can be anything. I'm using 100. This number here needs to be 20% of whatever you started with. That's why using 100 is kind of easy. And then you have an equation where you have to solve for t, and in the end you should get 51 years. Alright, we're going to practice that a little bit, but you should be able to come up with a exponential growth model or exponential decay model. So that formula is a good one to memorize.